you for such a nice introduction. It's a real privilege to be here with you tonight. I'm so excited to share some science with you, and it's great to see such a full house. For those that are just coming in, please have a seat anywhere you can find. Just checking the sound. Is it loud enough in the back? A little bit louder you want? Okay, thank you. We've got people to help me with that. Just give a thumbs up if you need it higher. Okay. I am really excited to see so many people here, and I think about how all of you could be home streaming Netflix right now, and instead you're here today with me to talk about science. So this is really exciting. I am here at the Aspen Center of Physics, attending this workshop on massive stars as cosmic change agents. And so tonight we're going to go on a journey talking about massive stars. I'm going to start by giving you some idea of what massive stars actually are, and then we're going to kind of zoom out in the universe to understand the impact these massive stars can have on their local environment, on their host galaxies, and on the greater universe. And so to start off, I want to begin with something that we're all very familiar with in terms of stars, and that's our own sun. In science, it's often a really good place to start with something that you know very well in order to be able to push out to different frontiers. And of course, in the stars component, the sun, obviously we know better than any other star in the universe. This is a movie from the Solar Observatory, or a time-lapse movie. It's not an animation. This is actual data of our star, the sun. And really, I just want to say that our sun is pretty unremarkable. It is an ordinary, everyday star, which is really great for us. We know it's this burning, ball of gas in the center, in the core of the sun, where it's very dense and the temperatures are very hot, millions of degrees. We have nuclear fusion, and that fusion produces enough energy to light up Earth, and we're really grateful for this, right? And the fact that it's an ordinary star, very stable and unremarkable, is great for us. It's allowed life to develop in a kind of a stable energy environment, and allowed so much that we know and love and is dear about Earth possible. But I want to delve into a little bit of the physics of the sun. So the fusion inside of the sun is basically taking hydrogen atoms. The sun is mostly hydrogen and helium, and you're taking hydrogen atoms. They've lost their electrons, and so really they're just protons. And in this really hot, dense environment, these little protons are being smashed together at high speeds. And eventually, some of those protons stick together, and if you get 4 of them to stick together with a couple of other changes and processes along the way, you end up turning out a helium nucleus. Right? This is the process of nuclear fusion. And if you take the raw ingredients, if you took your 4 hydrogen nuclei and you weighed it against your output, your helium nucleus, helium would weigh less. Right? This is a really interesting fact about nuclear fusion. And the missing mass has been converted to energy. This is just a statement of Einstein's famous E equals mc squared equation. The energy and mass sort of can transform into one another. And that energy from that fusion slowly makes its way out of the sun. And it's not a lot. There are so many nuclear reactions happening that it ends up generating a ton of energy. And as that energy, takes actually hundreds of thousands of years to go from the center of our star to the surface, at which point it flies free and some of it is intercepted by Earth. And this process in the sun goes very stable. It's very steady. It's very predictable. We think we understand it, which is really great. But I also just want to draw attention to this beautiful movie of the sun, because despite the fact that I'm saying it's pretty static and stable, there's a lot happening on the surface. You've got the convection cells of material kind of pushing up to the surface, making this beautiful granulated pattern. It's not exactly the same, but you can kind of think of it as like a bubbling part of water. And then you also have flares and ejection of material on the edges, kind of spewing some stuff out. Those are small scale effects, and it makes the sun quite beautiful. But the core of it is quite stable and predictable. Our sun is unremarkable, and stars can be formed in many, many masses. And one of the most interesting things in the universe that drives a lot of change are the massive stars. So to give you a sense of what a massive star is, this is a nearby star called Rigel. It's about 20 or so times the mass of our sun. Sun, this is not a real picture of the star. This is just an artist's conception. But it is to scale. So you get an immediate sense of the fact that it's a lot bigger than our star, than our sun. From this image, another thing that you can take away is that they're different colors. And this blue coloring of Rigel is, it is a piece of art, but it's meant to represent the scientifically accurate, the color of the star. And the color is a really important clue to the fact that these massive stars are not just more massive and bigger. They have intrinsically different properties. And the color actually ends up being related to its temperature. This is not just an astronomical phenomenon. We have this sort of experience that color and temperature are related here on Earth. You can go to just your fireplace and an ordinary fire. And in the center of the fire, where the fire is the hottest, you will see the flames are blue and white, and that color is reflecting the hottest part of the fire. And as you go to the edges and the flames, they turn yellow and orange and red. And this is reflecting the fact that those flames, that fire there is a little bit cooler. I mean, it's still super hot, right? It's still a fire. There's a temperature difference between the blue flames and the red ones. And this is the same in the color of stars. Rigel, which is a blue star here, about 25,000 degrees on its surface, is quite hot. And if you move to, say, yellow stars, much like our sun, it's only maybe 6,000 Kelvin. And if you go down into cooler and cooler colors like red, you end up with a star that's even cooler still. And so we know this just from physics, but you can also appreciate this in just as you look up into the night sky. This is an image from the Hubble Space Telescope, the fabulous Hubble Space Telescope, and I'll have more on that in a little bit. But this is an image from Hubble of a nearby star cluster in our own galaxy. One of the first things that you can see is that the stars are lots of different colors. And you can pick out just in this image which ones are hot and which ones are cool. And you can also kind of see which ones maybe are a little bit larger and a little bit smaller. But this just shows you that even from an image, from a scientific perspective, we can look at this and sort of put a temperature, put a thermometer on those stars. It isn't just from the Hubble that we see this. If it's a clear night tonight or tomorrow night, if you look up in the night sky with your naked eye, if you look carefully, you can actually see that the stars in the sky are different colors. And you can pick out the ones now that are hotter because they'll be the bluer ones versus the cooler, redder ones. Okay. But if you take those properties, I've told you that massive stars are bigger and hotter. You might be able to put those two together and think, well, maybe there are other things that are different about them. One of the key things that this adds up to is the fact that they're also a lot brighter. And to think about how bright a massive star is, I'm going to again anchor us to our own sun. And this isn't just for reference for us tonight. We use the sun in astrophysics as our kind of a key anchor point. The scales in astronomy are so large that even after decades of working with them, it's still kind of hard to get my head around it. So, and that's common. And so we use the properties of the sun as a unit of measurement. So we call the mass of our sun a solar mass, and we give it its own special unit. It's capital M with a double circle. That double circle is just the sign we use for the sun. So this is one solar mass, and this is how massive our sun is. And for reference, it's 10 to the 30 pounds. That's really awkward. I'm not going to go around doing that in my papers. So we use sun as a reference. All stars are measured in this unit. Galaxies are measured in the masses of our sun. And this gives us an intrinsic kind of intuitive feel for how big things are in the universe. Similarly, the brightness or the luminosity of our sun has its own special measurement. We call it one solar luminosity, or 1L with those double circles. That's our unit, and I want to show you what massive stars actually look like. This is my only table, so bear with me. A 4 solar mass star is 200 times the luminosity or the brightness of our sun. Only a little bit more massive, but significantly brighter. And if you go up in mass to 10 or maybe 50 solar masses, you're now at more than 1 million times brighter than our star. And at 100 solar masses, which is not exactly the cutoff, you can have stars more massive, but they're very rare. And so for practical purposes, we usually just put a cutoff of 100. It's more than 3 million times as bright as our sun. And some of these stars are so big that their radius would engulf the orbit of Mars. So these are really different beasts than our own stable, unremarkable sun. Okay, so there are a lot of facts and figures here, but if you put them together, they also imply one other thing that's really interesting about stars. You have a lot of mass in a massive star fueling this fusion, but the luminosity outshines what you might think just by looking at the change of mass. And that implies that there's something different about the nuclear fusion. And in fact, the center of these massive stars are even hotter and denser than our own sun. Temperatures are tens of millions of degrees. So that nuclear fusion skyrockets. The nuclear reaction rates just are wicked fast. And so that's creating the brighter luminosity. So you're burning through your fuel faster. You've got more fuel of it, but you're going really, really quickly, and you're producing a ton of energy, which makes this star really bright. That also means that its lifespan changes. You're running through the fuel super fast. And so one of the other things I want to put up here is how long these things live. Our sun will live about 10 billion years. Hallelujah, this is a great thing. 10,000 million years. If you go to, say, a 10 solar mass star, it only lives for 20 million years. And the most massive ones only live for a couple of million years. It's because they're burning through their fuel so quickly. That's just something to keep in perspective, is that it's a star just like our sun, but there are a lot of different properties. And the last thing I want to mention about massive stars is that they end their lives spectacularly. The nuclear fusion rates don't just turn hydrogen into helium. If you get, into the cores of these massive stars, you build up enough helium, and the helium starts fusing. It makes carbon and oxygen. And then the carbon and the oxygen start fusing, and you get silicon and magnesium and iron. And then eventually you have a runaway thermonuclear reaction, and the star blows up, supernova. And the supernova has another really dramatic effect on what massive stars can do. All of the elements that I was just, rattling off are not only formed in the core, but they're spewed out during the supernova, and more are formed in this very violent explosion. The brightness of a supernova is brighter than all of the stars of an entire galaxy combined. It doesn't last very long. It's a massive explosion. It's very bright. It's very violent. And it actually, distributes these elements throughout the galaxy. And this is really great, because it's these elements that form planets and that form the basis of life. But I'm going to I lied. I've got one more table to show you. So here's the periodic table. And I just want to briefly show this. It's color-coded by the source of how these elements are made. Just to emphasize, since we're talking about massive stars, all the ones in green, all the elements are green, are made through these exploding massive stars. So they have a pretty profound effect on what's out there in the universe. Okay, so that's kind of the sort of overview of massive stars. And I want to move into the fact that massive stars have a big impact on their host galaxies. Before I do, I want to pause and just see if there are any questions, any points to discuss around the properties of massive stars before I continue. I hope you're not all wishing you were watching Netflix.
Why are they so much hotter than you'd expect? Is it related to the gravitational pull at all? Or?
It's exactly related to the gravitational pull.
Question.
Oh yes, thank you for that. Why are they so much hotter than we expect? Is it related to the gravitational pull? And yes, what happens in these massive stars, what happens in any star, is that the gravity is pulling the star in. It's squishing it together as far as it can go. And it gets dense enough and hot enough that fusion starts. And that energy starts pushing out against gravity. And it reaches an equilibrium. If the energy wasn't enough, the star would squish and contract a little bit more, making it hotter and denser, and kicking up the nuclear fusion rate, which makes more energy and pushes it out. And between the pull in from gravity and the push out of that energy, it finds an equilibrium like our sun does, and it just sits there and churns. In massive stars, the gravity is so much stronger, and in order to support the star against its own gravitational collapse, you need to have a lot of energy. So, the phrase we use is hydrostatic equilibrium, but that is really the core physics on what's driving the higher reaction rates, is because if it doesn't, the star would implode, and as soon as it starts contracting, reaction rates kick up because it's denser and hotter and so on. Yes?
I appreciate the explanation about why it gets hotter and how it uses fuel and why that less luminosity. The projected lifespan of the star, is that math or is that measured? I don't really know anything about the field, so I'm asking.
Yeah, no, it's a great question. It's an excellent question. The question is, we know I'm saying these stars have short lifespans, and while the physical argument makes sense, have we measured it? And in fact, we have.
That's what,
Yeah, we've measured it. We've been able to measure this. In fact, we know a lot about stars. We know there's a lot that we don't know, obviously, but we have been able to actually measure, not to exquisite precision. I can't say it's 1.1 million plus or minus, blah, blah, blah. But yes, we have measured it, and we have measured the lifespan of a range of stars of a range of masses and different properties.
that's what these massive telescopes allow you to do. You can essentially, not exactly time lapse, but it gives you the ability to look at what's happened so many years ago and measure what happened now and then, right?
Yeah, the question is how we actually do it. If we use these big telescopes to be able to do it. And it's not a time lapse, you're right, it's not that. There are signatures of the birth and death of stars that we can measure. And some of them are from the great observatories in space, and some of them are from the great observatories on the Earth. And the really cool thing is it's not just one wavelength. We use the whole electromagnetic spectrum to look at different signatures of the birth and regular lifespan and death of stars. And you can piece together all the physics very carefully to be able to age date these things.
Very helpful, thank you.
Yeah, you bet. Okay. So we're going to move on to zooming out a little bit on the impact these massive stars have on their host galaxies. So here's a picture. This is art. This is not science. This is not a scientific image, but it's a picture of what a massive star could look like up close. It's blue. It's very hot. One of the things that it is blue in color, but it also radiates a lot of light, even higher energy than the blue in the visible wavelength. So it gives off a lot of ultraviolet light. And it's got so much energy that it pushes out that it actually starts driving material from the atmosphere of the star. It starts pushing its own stuff away. And you can kind of see this. It's not just a coronal effect, but you can see material kind of gently leaving the star. We call this a stellar wind. All stars have them. Our sun has one. But massive stars have them quite strong. So they lose a lot of mass. They're pushing this material out of their environment. And this has an impact on their their local birth area. So as we've kind of already talked about a little bit, stars are made from collapsing gas. The gas collapses in, starts nuclear fusion, and you have a star. Gas has to be cold to start collapsing, but this is how stars are formed. And once it's formed, the star actually starts clearing out its native birth cloud. And I want to show you what that process looks like a little bit. This is one of my favorite images in astronomy. This is the Pillars of Creation. This is taken from the Hubble Space Telescope. It's in optical light. It's a giant, giant cloud of gas in our own Milky Way galaxy. And when I say giant for scales, our entire solar system would fit in about a pixel on this image. Okay? Massive. And we call this a stellar nursery. You can't really see into the interior of the cloud, just like we can't see through clouds in our sky. But if you look carefully, you can see hints of stars forming interior to them. So you take a massive star, and its radiation will actually heat up the gas, and you can see little parts of this glowing, right? If you look carefully, these are stars hidden in those gas clouds heating. And eventually, with enough time, radiation from these stars will kind of push out the gas around it, and so we can actually see them more clearly. And just today, Space Telescope Science Institute, which is where I work, released some new video, a new projected imagery from the James Webb Space Telescope, showing a little of this process. So this is a brand new video that I wanted to share with you. We're using now the James Webb Space Telescope to peer inside one of those gas clouds. This is called the Cat's Paw Nebula. Inside here, just going to play it like this.
I need to enable the content.
Oh, thank you. That was not done. I appreciate the call out. Okay. So we're zooming now inside one of these molecular clouds, and you can see there's a massive star forming that's formed already in there, along with a bunch of other stars. And it's cleared out a cavity around it through its radiation and its stellar winds. And so you can see there are lots of other smaller stars being formed. these beautiful cavities are carved out primarily from the massive stars. And there may have been a supernova at some point going off, clearing out some of these too, but most of this is just to do with the small scale effects, the impact of a massive star. Just beautiful. Okay. Once the a big gas cloud is dispersed, we can see the stars more clearly, but it still has an impact on the gas around it. I mean, there's always gas in a galaxy. You may have dispersed this big, thick cloud. You still have a bunch of gas surrounding the star in the neighborhood. And these massive stars are hot enough that its ultraviolet light heats up the hydrogen gas around it and causes the hydrogen gas to glow. And this is what you're seeing here. You're seeing a bubble of glowing hydrogen gas, it's ionized hydrogen, and it's a cavity or a bubble that's been created by this massive star. So this ionized region is super hot. It's like 10,000 Kelvin. And you can imagine now not just one star, but stars are often formed in clusters. And so you can have a whole bunch of them forming in a star-forming region. And these bubbles that you can see here in kind of a reddish purple color, grow. They can overlap with the neighboring bubbles from other massive stars. They can merge. There's stars here that are not massive, that are not creating these hot bubbles of ionized gas. Maybe they're here, over there, and they might be stars just like our unremarkable sun. The massive stars are creating this effect. Okay, so now I want to zoom out just a little bit more. These are small regions, and I want to pull us out to the galaxy scale. So this is star-forming regions within a galaxy, and so let's look at a whole galaxy. This is a picture of Andromeda. This is our sibling, our sister galaxy. You know, I would love for us to be able to take a selfie of the Milky Way, but we can't, right? We don't have a selfie stick long enough to do that. But we can take an image of our sister galaxy, Andromeda. This is from a ground-based telescope. You know, we have a ton of amazing ground-based facilities as well. In fact, this image was taken from a telescope in Arizona. And most of the light you see here are from the stars. You have a bulge or nucleus in the center of this spiral galaxy. But a lot of it is just accumulation of all the stars in the Andromeda. But we're interested in massive stars. And so I want to change the filter on this. And I want to show you an image of the same galaxy, but seen in ultraviolet light, okay, which is what primarily only massive stars will give us. So this is an image of Andromeda from the Swift telescope, space telescope, in the ultraviolet. You do see the nucleus glowing as well, but everything else is really driven, the light you see is driven by these massive stars, and it's just gorgeous. See the structure of the galaxy differently. One other thing I forgot to mention. In addition to the stars, you also see these dark lanes here, right here, these dark colors. These are some of the areas of these big gas clouds that are the stellar nurseries, and then they're blocking out the light so you can't see them, but okay. So here's the massive stars. You can see it traces some of the spiral structure. It's quite beautiful. This is just the edge of the map. This funky shape is just where the observations turn off. Now I want to show you a little bit of a different view of Andromeda. I'm going to rotate the image a little bit and show it to you in a different ultraviolet light. This is from the Galaxies Space Telescope, another NASA mission that ended a few years back. And it shows a broader range of ultraviolet light. Just like in visual, we can have, red, blue, green, yellow. In ultraviolet, there's actually a range of colors too. And so this is a broader range. You can see more. Maybe the lower massive stars are shining in some of the other ultraviolet light too. But I like this not only because it's beautiful, but because it gives a little bit of sense of the shape of the galaxy. Right? These spiral galaxies are like a frisbee. They're disks. And you can see the spiral thing, but they're pretty thin. It's not quite edge on. You're seeing it at an angle. It gives you enough perspective to imagine that the light from these massive stars, a lot of the radiation is leaving the galaxy. It's leaving above the top of the galaxy and the bottom of the galaxy, and those ultraviolet light is now streaming freely through the universe. The massive stars aren't just carving out and impacting their local environment and making the galaxies glow in ultraviolet light. The ultraviolet light leaves the galaxies and can travel across the universe. The universe is incomprehensibly large. It truly is, to me, still, after all these years of studying it. And one of the remarkable things also, besides being incomprehensible large, is that when we look far away, we're also looking back in time. And so I know many of you might be familiar with this concept, but just to be clear, if there is a galaxy or a massive star 13 billion light years away, or on the other side of the universe, 13 billion light years away, it means that that light from that massive stars is taking 13 billion years to get to us. So whatever image we receive is what that star looked like 13 billion years ago. So it's this really amazing thing, because the universe is expanding, that when we're looking at very far distances, we can see the universe at very early times, when the galaxies were just babies, and then maybe they were toddlers and teenagers. We can really track the evolution of things through 13 billion years of time. Okay, so we're gonna move now into kind of backing up into that space. But before I do, I want to pause quickly and see if anybody has any questions about the galaxy part. Okay. This is my other favorite image in astronomy. This is the Hubble Deep Field. And I showed you Andromeda, which is our neighbor galaxy, very, very close up, very detailed observations. But the universe is, of course, filled with galaxies, billions and billions of them. And this image is a very special image. It was taken, well, first I'll just tell you what's in it. Almost everything that you see in here is a galaxy. Some of them are closer. You can see there's more structure. There's a spiral galaxy here and some stuff there. And we're seeing that structure because it's not as close in Andromeda, but it's relatively close. But even these little dots of light, almost all of those are galaxies too. They're just on the other side of the universe. They're just super far away, and so they look very tiny and very faint. Not all of them. As Vicki said in my introduction, I study little galaxies. I love little galaxies. And some of the light is coming from small galaxies that are closer to us, right? They're just intrinsically small. But at any rate, that's what we're looking at in this image. And I want to give you a little bit of history of this. Some of you may already know this story, but it's taken from the Hubble Space Telescope, which just celebrated its 35th birthday just a couple months ago. Hubble is amazing. It continues to produce unbelievably groundbreaking science. It's truly a gift that keeps on giving. It's our only telescope today that can see ultraviolet light. And it's the only telescope for the next 10 or 20 years that will be available to see ultraviolet light. So it is a very precious resource. We hope it has a continued long life. But when it was first launched into space, and side note, the mother of Hubble is Nancy Grace Roman, and this is the telescope that I work on now. She was the first chief of astronomy at NASA. Not only the first chief, but she's a woman, so in the 50s, 60s, that's pretty incredible. But she championed the idea of putting a telescope in space. And it's because of her tireless efforts over decades that we actually were able to get the Hubble Space Telescope, and that's one of the reasons why this new telescope is named after her. But okay, I digress. So we launched this thing 35 years ago, and we use Hubble, as well as really any other telescope that's been ever made, but through a competitive process. As a scientist, as other scientists in the audience, if you want to use Hubble, you have an idea, you write a proposal, you submit it, and it gets evaluated by an anonymous committee of your peers. I serve on these committees periodically. People take their turns. It's a very competitive process. 6 to 10% of proposals will get through, maybe 12%. But the director, the Space Telescope Science Institute, where the Operations Center happens for Hubble, is always given a little bit of time. And the director can choose to use this time however they want. It's usually for science that maybe the community won't propose for, or that's very important. It's for a variety of reasons. And this director said, I'm going to take Hubble and I'm going to point it at a blank piece of sky, and I'm going to stare there for 2 weeks. This was kind of controversial because we'd use amazing ground-based facilities to look at this little patch of space. And everyone's like, there's nothing there. You're wasting this precious resource for 2 weeks. You're crazy. Don't do it. The director persisted. This is the result. It wasn't a blank piece of sky. It has thousands and thousands of galaxies. And the field of view of Hubble is like a grain of sand held at an arm's length. That's the small little tiny patch of sky that Hubble sees. This transformed our understanding of the universe and of galaxies. For that, it's just a beautiful image, but it's really impactful to me. Okay, so this image, dots of galaxies, all of them have mass, almost all of them has massive stars, all producing this ultraviolet light that's now flying through the universe. This is projected in 2D though, right? We're just a projection of the sky. We can, through sophisticated techniques, separate them out as a function of distance, though. So we can actually build a 3D map of the universe. And I want to show you a schematic of what that looks like. So this is now not just in space, but also a time diagram of the universe. The left, we have the Big Bang, 13.8 billion years ago. And on the right is today. And so what you're seeing here is the Big Bang happened, and the universe was super hot and dense. We went through a rapid period of expansion, which we call inflation, which we don't really understand, but it's got a cool name. And the universe was really cooling at that point. And, you know, the universe was populated by a lot of funky subatomic particles, quarks, and things that are outside of my area of expertise, quite frankly. But then as things started to cool, those interesting particles started combining and making protons and electrons and things that sound a little bit more familiar. But it was like and then they started combining to make hydrogen and helium, neutral gas. So the electrons and the protons are now just, you know, a hydrogen atom or a helium atom. That's all there really was. So you've got thick neutral gas. And the light, there's not a lot of light going through them. The light gets trapped, and we call this the dark ages. The universe continues to expand and cool. And I think you know where I'm going. As it gets cooler and cooler, gas starts collapsing. And there's some dark matter involved that's driving that's, you know, the primary source of gravity. That's another whole different talk. But we're just going to know that there's dark matter in there, and it's pulling the gas together. So where I'm going is this cold gas starts collapsing, and you start forming stars. Start forming galaxies. And that's the epoch here, where you really have the first stars about 400 million years after the Big Bang. And they continue to evolve. You've got the baby galaxies, now they're toddlers as you're moving across through time. They're developing, and now you're getting planet formation, and you end up at the present day here. All the time the universe is expanding, and that's what this graph is meant to show, is that you're getting bigger. The galaxies are getting farther apart, the universe is getting colder. Okay. Let's focus now on this early time period where the first galaxies are forming. Hubble was able to see, not quite back that far, Hubble was able to see back maybe here. With the new James Webb Space Telescope, we've got a bigger mirror. We can see farther, faster, fainter, more clearly. And so we can start to see earlier and earlier. One of the things that we're really learning in great detail is that the mass of stars in the early universe transformed the physical state of the universe. We went from neutral gas permeating the universe in between galaxies in the intergalactic space, having ionized gas heated by these massive stars. So all the galaxies at this point are bathed in this intergalactic starlight. And the epoch that we're talking about is kind of in here. We give it a special name. We call it the epoch of reionization. It's the last great phase change of the universe. And so today we live in a predominantly ionized universe. This process happened over time. And I have a movie here for you to kind of demonstrate what this looks like. We're going to watch a simulation from a team called the Renaissance Simulation Group. It's cutting edge, computational simulation that's just been released in the last couple of years. And to make a simulation like this, you take all the laws of physics, you code up equations in your computer, and you let it run, and it visualizes what the universe was supposed to look like. And then, of course, we use this as a tool to compare it to real observations to see if we understand things. What you're going to see here is just a short snap of the history of the universe when we're going to go through this epoch of reionization. The colors represent different things. White is more of just the neutral gas, the starting point. The red represents hot gas or ionized gas and stars. The green are all of the chemical elements that the supernova has erupted and pushed out into the universe. So we're going to play this, and if people are interested, I can do it twice. Oh, I might need to restart things, but I can try to do it twice. So you're going to start off in the dark ages, when the first stars are forming, and what you're seeing here in white is the neutral hydrogen, is the neutral gas, and you're starting to see galaxies. This is way zoomed out. The galaxies are like way down here in these little points of light. The galaxies, the massive stars, are heating the gas, ionizing the gas, creating these
not just regional bubbles, but they're now creating these giant bubbles around the galaxies. The supernova exploding, they're spewing oxygen and carbon and iron and magnesium out into the universe. The bubbles are going to get bigger and bigger. This is a short period of time in the universe, and it won't fully finish the epic of reionization when the video finishes, but you'll get a sense of the impact, and this just gets, these bubbles get bigger and bigger until they all merge together. Now, the simulation is going to switch here, and it's going to show you component by component. So first, we're going to see just the neutral gas in white, I think. Okay. So we're getting a little visualization here. So these are these elements of neutral gas that have collapsed around the dark matter. These are the stars forming in the galaxies and the ionizing radiation being pushed out on the galaxies. Now this is the ionized gas. These are these beautiful bubbles that are engulfing many galaxies at once. Just a sort of a visualization of just heated gas, maybe not ionized, but it's still hot. And here are the heavy elements from supernova, the green, that are now just everywhere. And this is, thank goodness for this, because this is where the planet formation comes from. And so now you're seeing all the multiple phases mixed together. We can't see this in observations, right? You can only really look at one piece of this at a time and hope to put it together. That's one of the beautiful gifts of simulations, is that you can have it all together all at once. Okay, I want to pause there and see if anybody has any questions. I've thrown a lot of material at you. Yes?
During the epic period, you showed on the three-dimensional graph.
Yes.
Just from a density perspective, I think what you're saying is that there are an enormous number of objects in that period, and they essentially consolidated somewhere late in that period and formed much larger masses of objects. And is it the gravitational push between each of them that spreads them out in the universe and pushes them away from each other?
So the question was, first was a confirmation that in this epic, what I was saying is that it's the cumulative impact of all of the galaxies that create this epic of reionization. And that's exactly right, and that's where we're going. In fact, we're going to go in a little bit more detail about that. And the second is that really about the spaces between galaxies getting bigger and what drives that. That's a really interesting question. You know, we think that from the Big Bang and the expansion of the universe was driving it, and that was the basic theory for a long time, until about 25 years ago or so, maybe a little longer, 35, anyway, a couple decades ago. There was a measurement that showed that the universe wasn't just expanding, but the expansion was accelerating. And this is really bizarre, that there's some sort of pressure or force that's making the universe, you know, one might think from the Big Bang that, you know, big explosion, it expands outwards, it cools, the expansion slows, and maybe it would contract back in and you'd have a big crunch, and then maybe it happens again. Nobody really knew. You know, still an unknown question, open question. But now we've measured the fact that it's not just this acceleration, the expansion isn't slowing down, it's actually getting faster. Call this dark energy. We don't know what it is. The Nancy Grace Roman Space Telescope is built in part to try and answer that question. Okay, but another question in the back there.
Thank you. So when you're talking about light, you're talking about the visible spectrum, and related to that, I'm just wondering, because you mentioned earlier that the supermassive stars are producing ultraviolet light, which essentially has an effect on other gases, where it's going to be absorbed and then re-radiated as visible light. So how does that story fit into the light here?
Excellent question. So the question was about framing that the massive stars produce a lot of ultraviolet light. Some of that light get absorbed by other things in a galaxy, other gas or in the universe, and re-radiated at maybe visible light or longer wavelengths. Yes, the story is more complex. The massive stars produce the most of their light in ultraviolet and blue light. They also, just to make, to be comprehensive here, put out light in all of the spectrum of the visible wavelength. So, if you were to see a massive star without being able to see ultraviolet light with your eyes, you'd still see it because it'd be producing a lot of red and yellow light too. It's just predominantly ultraviolet. As that light expands, as that light travels out, It will hit gas and will be absorbed by the gas. It will hit dust grains and be absorbed by the dust grains, and basically heating those elements, and then those elements re-radiate some of the light longer wavelengths, whether it's visible or infrared, far infrared. And so we think about this energy radiation being processed through multiple parts of a galaxy. And that's exactly right. And that's going to build into the story I'm going to tell you about in a second. That's an excellent point. Yes. Thank you.
It's a basic question, but that famous Hubble picture,
Yes.
why does that take 2 weeks? Why can't you take it in a moment? I don't understand.
Oh my gosh, that's a great question. Thank you for that. Because if you looked up at this patch of, thank you, repeat the question. The question was, why does it take 2 weeks to make a picture like this? Why can't we just look up at the sky and snap an image and see this? And it's because if you were to look up at the night sky, at this particular patch of sky, you would not see anything. It would be dark. Reason we can't, because the objects in here are so faint. So if you think about taking a picture, inside, you might want to use a flash because the camera's not going to pick up the image in a dark room. But if you set the camera like the old-fashioned cameras, you left the camera open for a really, really long time, it would pick up the image. It would still be faint in a dark room, but you'd have to expose the film for a really, really long time to see in the dark. You can use a flash now, but this is the same thing. The galaxies are so far away and so faint. Unless you open up the shutter of your camera and just collect as many light rays as you possibly can, you won't see anything. They're just too faint. Does that make sense? Okay, yes.
That image has a beautiful range of different colors of galaxies. Is that related to redshift, or is that related somehow to the types of gases that are being formed in the stars in those galaxies?
Oh, great questions. The question was about the colors of the galaxies in here. Is this redshift? Is this related to the gases in the galaxies? There's a two-part answer. First part is that in particularly the bigger ones, the one that's more structure, color is based on what types of stars are there. So all of this, all of the spiral galaxies you see are kind of blue, and that's because spiral galaxies host a lot of massive stars, just like Andromeda. There are these other funky-looking galaxies. They're ellipticals. They look kind of like a football. And these are decidedly not blue, right? These are red and orange. They don't have a lot of massive stars. They don't have a lot of young stars at all. These are all old stars, and they're small or lower mass. They're more like our sun. And so the stars in these galaxies are not making a lot of ultraviolet or blue light. And so what you're seeing here is the cumulative sum of the light of the stars. Not really the gas. It's really driven by the stars. And so that tells us a lot about what's happening in that galaxy. I see this, that's a star-forming galaxy. It's got a lot of massive stuff going on. And some of the stuff that's farther away has a different color because of its redshift. And so if you take a bright blue galaxy with lots of massive stars like Andromeda, and you were to put it on the other side of the universe, the light that would reach us has been stretched and redshifted into longer wavelengths of light. If you take an image today of an Andromeda on the other side of the universe, that picture is going to be red or even like infrared. That's what's so amazing about the James Webb Space Telescope. It's an infrared telescope, and so it allows us to see massive stars way in the early universe. The massive stars in the early universe are producing ultraviolet light, but when it reaches us, it's now infrared light. So that's just a really cool thing about the universe. Yeah. Yes?
If people could see like ultraviolet light, how much brighter would the sun and other stars?
If we could see an ultraviolet light, our sun would be really dim. Because our sun, being just your average, remarkable star, produces most of its light in the visible wavelengths that we see. Most of it comes out in the yellow and the orange colors. So if we could see ultraviolet, we wouldn't really be able to see our sun very much. In fact, as a side note, the reason our eyes are developed to see in the visible is because that's what our star produces. And so from an evolutionary standpoint, the cones in our eyes were developed to be most sensitive to the wavelength of light that our star sun makes the most of. But if you could look out, if you could see an ultraviolet light, you could see other massive stars maybe in our neighborhood around the Milky Way. So that would be, but it's kind of a cool thing to think about. Okay. Oh, we got another one.
What is is the latest thinking of the mass of galaxies found outside of the Big Bang?
Galaxies come in a wide range of masses. Our own Milky Way is about 10-ish so billion times the mass of our sun. There's that unit. We measure masses of galaxies in units of our sun. 10-ish billions or so. We have the galaxies I study can be millions of times smaller, come at a range of scales. They aren't born big, they're born small, and they grow bigger as a function of time. And on that, I'm going to move to some images from the James Webb Space Telescope of the early universe that shows the mass of galaxies. And so shown here are Webb images. This is the beginning of a deep field for Webb, right? It's only been up for a couple years. We're working on it. What we're looking for here, we see galaxies close, but what we're really looking at in this images are the ones that are very, very far away. Also, because we want to understand the masses, but also want to understand this epoch of reionization. So we know it happened. We know the epoch of reionization happened. We know how many rays of UV light were needed to make that happen. And so for a long time, for many years, we've done the Hubble Deep Field, and we go out and we try to count the galaxies in the early universe and say, okay, these galaxies have so many massive stars, have made so much UV light. We do all that math. We don't have enough UV light to ionize the universe. There's a bunch of photons missing. One of the leading ideas that has been going for quite a while is that, well, what if there are little galaxies in the early universe that are too small and faint for even Hubble to see? If there are a lot of them, collectively, they might make up the difference. And so Webb is now starting to probe this parameter space. And this recent result, just came out this past year, has identified two little galaxies, 1 and 2, here's a zoom in of them, that have very low mass galaxies that we've never been able to see before without Webb. This is one here, this little red smudge, probably got a lot of ultraviolet light in the early universe. Here's another one, that little dot. We've managed to count up enough of them that it's looking like these little galaxies actually dominated and drove this epoch of reionization. Right? So that's really neat. This is one of the cool results coming from Webb. There's another part to the story, but I think I'm just about out of time. So I was going to share a little bit more about little galaxies. I think we might be saturated anyway. But I do want to close with a thought to the future. And so I'm just going to skip over a little bit here. I'll just pause for a minute. This is what a low-mass galaxy looks like in the nearby universe from the ground, from a ground-based telescope. We're zooming in to see what it looks like, part of it with James Webb. As we go all the way, all these little tiny white specks of light are individual stars in this other galaxy. There's a foreground star in our Milky Way, there's some background galaxies, but if you were in this other galaxy and were looking up at the night sky, these are the stars that you would see, which I just think is fantastic. Okay, but I'll skip over just the end, and I just want to say a shout out to the Nancy Grace Roman Space Telescope and the mission head for the Science Operations Center. This is a graphic image of what it looks like. It's due to launch next year, funding permitted. And to show you what it's capable of, it's very similar to Hubble in its image quality, but what it's capable of is quite different. I'm going to go back to the pillars of creation that I showed you earlier in the talk. This is the Hubble image, overlaid on a wider picture of this gas cloud taken from the ground. And as we zoom out on this ground-based image, I'm showing you one field of view for Roman. So Hubble can see this little tiny patch. Roman can see a couple hundred times the scale of Hubble. So with Roman, we are going to get a totally different view of the universe that is complementary but unique to Hubble and Webb, as well as any other facility we have going. I want to mention before I close that most of the work that you've seen here, a good chunk of it, was funded by the National Science Foundation and by NASA, which is ultimately funded by our federal government. And so if you are interested and really are a proponent of science You might want to make your voices heard in your local districts to make sure that the funding for this incredible science continues. When I say the funding pays for people. You don't have a lot of lab space or a lot of material or things. What the funding goes is to pay students, postdocs, and researchers developing the skills that not only forward science, but also invest in technology and innovation, many different areas related to data in our country. Okay, thank you for being such an amazing audience. Yes.
Correct me if I'm wrong, you say that James Webb is the only telescope to date that could detect UV light.
It's a little different than that.
Question or repetition?
Oh, yeah, sorry, thank you.
Let me do the follow-up question. Will Roman be what James Webb?
Excellent. The question was, can Webb is the telescope that can only detect ultraviolet light? And almost, it's Hubble.
I mean Hubble.
Yeah, okay, it's Hubble is the only telescope that can detect ultraviolet light. Roman will not detect ultraviolet light. That was the second part of the question. Roman is optical and near infrared. And so it's really set up to probe the distance universe to be able to measure this dark energy. And it actually is expected to be able to detect tens of thousands of supernovae at very, very far distances from us because of its infrared capability and wide field of view. But no UV technology from Roman. There's another telescope on the horizon. It's called Habitable Worlds Observatory. And it's a concept still. It's just beginning to develop. That is meant to be able to do ultraviolet light. And one of its prime missions, just like the name would suggest, is to search for habitable worlds. Roman is actually got technology that's a precursor to it. Roman will detect hundreds of thousands of planets around stars in our Milky Way, and has a special technology called a coronagraph, which blocks out the light of a star to be able to directly image a planet orbiting a star other than our sun in the Milky Way. And that technology in space will seed future development for habitable worlds that we'll see in the ultraviolet.
So there will be more questions. Kristin made time during her talk for questions. I know some people need to catch a bus. Let's take a few questions. You can manage them yourself.
Yeah, I'm happy. If people need to leave to make a bus, no problem. I'm happy to take more questions, though, if people want to stay. Yes?
I'm curious, are there any astronomers who are questioning whether the Big Bang actually happened?
Always. We wouldn't be scientists if we weren't questioning. Oh, are there, thank you. I'm so sorry, Vicki. Do we question the existence of the Big Bang? And I would say always. There are scientists, it's our job to be skeptical, to ask questions. And this isn't my area of study, but there's all kinds of physicists thinking about, alternative scenarios. Yeah. But all roads right now, all evidence that we have are in support of a Big Bang. And so to overturn widely accepted theory like that, you need very, very strong evidence. It's just kind of the standard scientific method. So it's one of the fun parts of being a scientist. You can probe and question, but you do need to find some pretty significant evidence to overturn a theory that has supported by multiple lines of observation. But yeah, people think about it. Yes?
To what extent does black hole physics play a role in what you're telling us? And also, how early on your three-dimensional plot is it thought that black holes were appearing?
Oh, these are great questions. The question is, how do black holes factor into what we've been talking about? How early do they form on my 3D plot on the timeline of the universe? Well, black holes factor into this quite a bit because oftentimes the remnant of one of these supernovae that go off or a massive star, once it ends its life, it can actually become a black hole. And so that's one of the end states of a massive star, is to make a small black hole. One of the things that James Webb has discovered, or the observations from Webb has discovered, okay, so let me step back a minute. That would be a little black hole, right? A solar mass sized black hole, or a couple solar masses black hole, or 10 solar mass black hole, which we just learned about this week from Vicki. But you can also have much bigger black holes. And in the center of most galaxies in the present day universe, we think there are supermassive black holes. We're great at naming in astronomy. That's the official name. So in the middle of our Milky Way, we have a supermassive black hole that we think is 1,000,000 times the mass of a sun. One of the surprising things from Webb is that we're finding evidence of these really massive black holes in the very early universe. And this is fun for us because how did they get there that fast? How do you make a supermassive black hole within a few 100 million years after the Big Bang? We're not really sure, but it's exciting. And so massive stars make black holes, but there are supermassive black holes that are formed through other pathways, and apparently they exist very early in the universe, and we don't know why yet.
In your diagram, how early?
How early? I would say at the same time when these first stars were starting, about 400 million years, they're forming right here too. That's how, the question was how early, and it's that early. Okay, I think I saw a hand up over there.
You said essentially that in order to have star formation, we need cold gases, and in the era of reionization, there was UV light that was heating everything up. So does that kind of slow down star formation, or how does that play out?
In fact, it did. Oh, thank you. I am so bad at that. The question was, if you need cold gas to form stars, in the early universe, you've got all this hot ultraviolet light, it gives. And that's the part of the talk that I skipped over. It's a paradox. Stars formed in little galaxies, the stars forming in little galaxies contributed the most to this epoch of reionization. That transformation stopped the stars from forming in these same galaxies. And so that's actually, if you think about the heat from all of the ultraviolet light in these massive stars, many of which were coming from small galaxies, it not only permeates the universe, but that UV photon then zaps a little galaxy, heats it up, and you need really, really cold gas to form a star, and so there the star formation stops. That's been an active area of my research, to try to understand that process, and it feeds into questions about how big do you have to be as a galaxy to survive that epoch of reionization? What does your future look like? And we do this work in an odd way. If you look at the early universe in this picture, it's rich with information, but if I want to study the details of this little galaxy, that's all the information I have. Not a lot to go on. The work that I do actually looks for what a galaxy like that might look like today, and do a kind of an archaeological dig on the stars in that galaxy to try to find the ones that formed then. So you remember in the beginning of our time together, I said that our star, the sun, will live for 10 billion years. Some of the stars that formed in the very early universe have evolved for 13 billion years, and they're still present. There are stars in our neighborhood in the Milky Way galaxy that are 13 billion years old. So what I do is I look at these little galaxies nearby, called WLM, this is just a size comparison, and I look at the stars with the James Webb Space Telescope, and I dig around to try and figure out, I age date the stars, and I try and pull out when the stars were formed as a function of time, okay? I can do that by using their color, their brightness, and from an image like this, you actually can make a diagram that looks like this. This is from one of my papers. Brightness of the stars versus their color, each dot represents the measurement of an individual star in that galaxy. So blue colors are over here. These would be the bright blue stars, or those massive ones we're talking about. Our sun might sit down here, or even actually maybe over here a little bit, at any rate. This diagram has a lot of structure in it, and we can, from this diagram, I can age date and create a birth rate over the universe for this galaxy. And my analogy for this would be thinking about the human population. If you have a small town USA, you pull everybody out on the main street, you take their picture, you can use what you know about human evolution to approximately age date these people. You can find the babies, the toddlers, the teenagers, the adults, the senior citizens, and you could create the birth rate over about 100 years, the lifespan of a human for this town. This is the same thing we do with this diagram, and we can see how many of those stars were formed during the epoch of reionization, which is here. And one of the interesting things that we're finding is that the galaxy, this little galaxy made stars, but then that heat stopped it, and over billions, probably 5 or 6 billion years, really didn't make very many more stars anymore. There's this interplay between the heat and the impact. So it's this paradox. But we've been measuring this in more and more small galaxies by doing this kind of archaeological dig in nearby galaxies. And so it's quite complementary to what we see from James Webb at the high redshift universe. We can't do these detailed studies.
At the end of this beautiful story, let's thank our speaker.